Hello everyone. This is topic 7 for exam 1, integrals involving and resulting in exponential functions. So we're still just thinking of integration as anti-differentiation and involving the exponential functions. For example, the derivative with respect to x of e to the x we know is e to the x. So if we want to reverse that process, again, integration is the reverse of differentiation or anti-differentiation. If we want to integrate something of the form e to the x with respect to x, then that should bring us back to e to the x. So that's our first new formula. The integral of e to the x with respect to x is e to the x, and of course we include our constant of integration, so plus c. And then we have the chain rule version, and we have the disclaimer here, let u be a differentiable function of x. So if we have something that fits the form of e to the u with respect to u, as long as we make the appropriate change of variables or u substitution, or we pick u to be the power on e and satisfy the du, then the integral of e to the u with respect to u should become e to the u plus our constant. So those are two new formulas you'll have to memorize. And in our first example, something rather simple, because the power on e is linear, but it still requires a u substitution, so we're going to pick u to be 5x. The differential du then is 5 dx, and we modify to get 1/5 du is the differential dx. So if we look back at the integral, we're trying to fit the form of e to the u by choosing u to be 5x, and the only thing left over is the differential dx. And comparing that to the du, we see that the dx makes up 1/5 du. So we could fit the basic formula, bring out the 1/5 most efficiently. Integral change of variables gives us e to the u with respect to u. And so integrating, the 1/5 tags along, e to the u integrates to be e to the u. We had our constant of integration at that point. And then back substituting, we have 1/5 e to the u was 5x, and then plus our constant. But this is a very special case because the argument, as I mentioned, is linear. So the 5x, that's a linear argument. And if we have a linear argument, just think of the situation where maybe instead of a 5, this is a 7. Well, the only thing that's going to happen is all of these 5s become 7s. And so therefore, in general, we could write the formula that the integral of e to the kx with respect to x, okay, just like our linear argument rules for trigonometric functions, it fits the integrable form, and so we get back its respective antiderivative, but modified by 1/k. So 1/k e to the kx plus our constant. So when we have a situation where we have e raised to a linear power, that's the way we should integrate, by inspection essentially. Because, well, there's two reasons. In about 3 more weeks, we'll be integrating those things on a daily basis, and we don't want to have to go through a formal u substitution every time. And the second reason is if I give you a question like number 2, you would actually have to perform 3 u substitutions if you did not accept what I'm referring to as the linear argument rule. Because they all fit the form of e to the u. Well, first thing we should check is the fact that we have a string of terms, so we know by the sum and difference rule we can integrate term by term, and we also know by the constant multiple rule that these constants tag along in the integration process. So our job is to make sure that each of the variable factors involved in the terms fit in integrable form. And they do. They're all of the form e to the u, but moreover, they're of the form e to the kx, because the powers are linear. So therefore, if you accept the linear argument rules, you can integrate by inspection. Otherwise, again, 3 separate u substitutions, picking u to be 6x, negative 2x, and 3x respectively. You have to go through all this work for each one of them. Where if we understand the linear argument rule, term by term, the 3 tags along, integrating e to the 6x, and with regards to the formula e to the kx, we get 1 over k e to the kx. So k is 6, so we get 1/6 e to the 6x. Go to the next term, plus 4 tags along. E to the negative 2x would integrate to be 1 over negative 2, e to the negative 2x, and then finally minus 12 tags along, and e to the 3x would be 1/3 e to the 3x. Then I'll squeeze in the constant there. And so then simplifying, we get 1/2 e to the 6x minus 2 e to the negative 2x, and then minus 4 e to the 3x plus our constant. So when the power on e is linear, I would strongly suggest the linear argument rule in integrating by inspection. But if the power on e is not linear, then I would suggest a formal u substitution. And remember when we had algebraic functions mixed with trigonometric functions, we said the trig functions dominate. And the same thing with algebraics and exponentials. The exponentials functions dominate over the algebraics. And also recall I mentioned this acronym, my 8, that we're going to be using as a hierarchy. L stands for log, I for inverse trig, A for algebraic, T for standard trigonometric, and E for exponential. Right now the purpose is just to talk about the 5 main classes of functions, and later on, as I said, we'll use that as a hierarchy. But with regards to algebraics and exponentials, exponentials dominate. So when we look at this problem, our focus should be on e, and we could ask, do we have a formula for e to the u? And we do, so let's try the u substitution. Pick our u to be the power on e, 1 minus x cubed. The du is minus 3x squared dx. Modifying, we get negative 1/3 du is x squared dx. Going back to the integral, we've already accounted for e to the u. The leftovers are x squared and the differential dx. And comparing them to our du, we see that they match, just modified by the negative 1/3. So replace those factors by negative 1/3 du. We've accounted for all factors in the integrand, so we're ready for a change of variables. We'll bring out the negative 1/3, and upon the change of variables, we have the integral of e to the u with respect to u. And remember, with this u substitution process, you should always bring it to a point where it fits the basic formula, because then there's only 2 steps left, integration and back substitution. And in this case, the negative 1/3 tags along, integrating e to the u, we get e to the u, we had our constant of integration at that point, and then back substitute. So negative 1/3 e to the u was 1 minus x cubed, and then plus our constant. Okay, so algebraics and e's, the algebraics dominate. And here's an example where the algebraic factor involved is a little bit more complicated, but we do see an e involved as well. So we have to trust And maybe it would be efficient, instead of rewriting this, instead of having it as e to the square root of x over the square root of x, since e dominates, let's write it as 1 over the square root of x times e to the square root of x. And then consider the fact that, again, e dominates over the algebraics. So we could try to fit the form of e to the u by choosing our u to be the square root of x, the power on that base of e. So bring it off to the side here, choose u to be the square root of x. Okay, now we just have to be a little bit more careful in terms of our differentiation. When u is a polynomial, like in example 3, it was relatively easy because polynomials, in terms of calculating the du and such, because polynomials are the friendliest functions around. When you have radicals or rational functions, you just have to exercise a little bit more care. As in this case, where u is the square root of x, which we'll need to rewrite as x to the 1/2. The du then is 1/2 x power 1 less, negative 1/2. Formally, don't forget the differential dx. And we can modify by the 1/2. And you could think of dividing both sides by 1/2, or maybe more efficiently multiplying both sides by 2. So 2 du would be, and then at the same time we do that, let's get rid of the negative exponent on x to the negative 1/2 and make it 1 over x to the positive 1/2. And if that's not enough to see that the leftover factors are in fact what we have here, that equals 2 du, you could put the x to the 1/2 back as the square root of x. So 2 du is 1 over square root of x differential dx. And now reflecting back on the integral, you see that the leftovers, 1 over the square root of x and the differential dx, do in fact match our du here, just modified by the 2. So replace those by 2 du. And all factors are accounted for, because we were shooting for the form e to the u, by choosing u to be the square root of x. And so change of variables to integral e to the u with respect to u. So there's our basic formula. Integrate, we get 2e to the u at our constant of integration, and back substitute. So 2e to the square root of x, and then plus our constant of integration. Okay, so just one more page of examples, but it will show us all the different situations we might encounter when the exponential function is involved in the integration process. So in example 5 and in example 6, we see exponential functions with trig functions. Now, we just talked about how exponential functions and algebraic functions, the exponentials dominate. But when you have exponentials and trigs, you don't know which one dominates. You have to try something. And in this case, I'll just break out a piece of scrap paper here. We have two choices, obviously. In either of these questions, 5 or 6, we see that we have e's, so it could be e to the u, and we have a cosecant squared, so it could be the integral of cosecant squared of u, which, recall, results in minus cotangent of u. Then e to the u, of course, is e to the u when integrated. So we have a choice. So we have to decide which one is which. In the first example, number 5 that is, if we were to choose our u, if we were to choose to try to fit the form for e to the u, then we would have to pick our u to be the power on this e, 3x. Because this e to the 3x, remember, belongs to this cosecant squared. Remember, it's cosecant squared of this quantity. So that's the argument or the angle that belongs to the cosecant squared. So if it's going to fit the form e to the u, this would be the e we would be focusing on, and our choice of u would have to be 3x. And we know the du needs to be satisfied, and so good luck generating all of this to be the du. So it should be pretty apparent then that e to the u is not the correct formula, and we would have to choose our u, or we would choose to try to fit the form for cosecant squared of u by choosing our u to be e to the 3x. So, doing so, we calculate our differential du. Make sure you put yourself in the differentiation mode. The derivative of e to the 3x is e to the 3x times 3. And the differential dx as well, we can modify by the 3, so we have that 1/3 du is e to the 3x times the differential dx. And looking back at the integral, to make the change of variables, we see that we tried to fit the form of cosecant squared of u. The leftover factors are e to the 3x and the differential dx. We compare those to our du, and we see that they match, just modified by the 1/3. So we replace e to the 3x dx by 1/3 du. We've now accounted for all the factors of the integrand, and we can make the change of variables. So we'll bring out the 1/3 integral, and the basic formula now is cosecant squared of u with respect to u. And hopefully you've memorized them. Cosecant squared integrates to be minus cotangent of u, get our constant at that point, and then back substitute, so negative 1/3 cotangent of the u was e to the 3x plus our constant. Okay, so then for question number 6, again we see a product of exponentials and trigs, and as I mentioned, we don't know which one dominates. It's not like exponentials and algebraics. So we have to try something. And again, the only choices, as we wrote down a few minutes ago, are e to the u and cosecant squared of u. If you tried to fit cosecant squared of u like we did in the last example, your u would have to be 3x, and then good luck generating this part to be the du. So it's usually pretty obvious which one is not going to work. So in this case, the one that will work, or that we would expect to work, is going to be e to the u. And that is by choosing u to be the cotangent of 3x. Okay, and then differentiate, derivative of cotangent minus cosecant squared, same argument 3x, don't forget, times 3, the derivative of the argument as well as the differential dx. We can routinely modify by the negative and the 3, so negative 1/3 du is cosecant squared of 3x times the differential dx. So now when we reflect back on the integral, we were trying to fit the form of e to the u. We've accounted for that, and the leftovers, cosecant squared 3x dx, we compare to our du, and it shouldn't be any surprise that things match, just modified by the negative 1/3 in this case. So replace those factors by negative 1/3 du, and we're ready for the change of variables. And so, again, the most efficient thing, bring the constant multiple, negative 1/3 in this case, out in front of the integral, and the change of variables gives us the basic formula for e to the u with respect to u. And so then we can integrate. Negative 1/3 e to the u integrates to be e to the u at our constant, and then finally back substitute. So negative 1/3 e to the u was cotangent of 3x plus our constant. Okay, I've got 4 more examples to go through. We're at the 20-minute mark, so I'm going to do this in 2 parts. We'll stop right there for this part, and we'll come back and look at the rest of the situations that we can encounter when we have the exponential function e involved in the integrand. So we'll see you for part 2 when you're ready.